In this recording, we're going to look at 3 questions, mainly about diacid titration and dibase titration. And these questions get into a lot of details of calculations within drawing the curve of diacids and pHs at any particular volume of OH minus, for example, added for that diacid. Question 51, we can actually extrapolate from a curve and probably given pH values, the pKa1 and pKa2 from the data given. Question 52, we will detail the dibase titration and look at again the pH at different volumes of acid added. The first question, this is the order I do 51 and then number 50, because 51 has a lot of detail, so 50 will go faster. So 51 says I have carbonic acid, H2 carbonate. I have 10 milliliters of it with a known concentration, and we're adding to that carbonate, hydrogen carbonate, we're adding, or carbonic acid, you can call it too. This is actually carbonic acid. We're adding NaOH. We're given also the pKa1 and the pKa2 of the couples of the two reactions, not the two reactions, the 2Ka reactions for the diacid. The degree of the progression of the titration is described by X, which is the volume of the base added divided by the volume at the first equivalence. And we're asked to calculate the pH at each of these, which is quite a lot, of volumes of NaOH added. At first thought, right away when you see a chart like this, or no chart, whenever you see X is equal to 1, that is my equivalence point. So I don't actually have to go and calculate V at equivalence, which is the first step you would usually do for any type of titration reaction. Here I don't have to, automatically X is 1, my first equivalence is thus 5. Automatically 2, 5 milliliters is my first without any calculation. 10 milliliters will be my second equivalence point, and of course here X will be 2. When X is equal to 0.5, this volume is the half equivalence point. At 1.5, this is the second half equivalence when X is 1.5. So those are automatics. Okay, we're just gonna detail some of the graph of diacids. The first thing you should notice is indeed this is an acid titration because we start off with a low pH. Then we have two rises in the pH value. Okay, so this is the first rise at the first equivalence point, and we have here a second rise of the pH at the second equivalence point. So this is a diacid graph and titration curve. Also, I just want to point out that the reaction from here, start H2A, will look up until here. So here we have the pKa1 at the half equivalence. And then at the equivalence point, all of the H2A becomes converted to HA minus. And this actually, it looks like a single, up until here, kind of, if you forget this area all the way, just concentrate on this part, this looks like a monoprotic acid titration curve. And it's a weak acid because I have this initiation of pH, so a small increase, and then a buffer region on this end where there's hardly any change in the pH. Remember, with weak acids, when I used to get the A minus on this end, after the first equivalence or the V equivalence, the OH minus was in excess. In this case, no. The OH minus can react further with the HA minus and creating another weak acid titration graph. So again, here's my new initiation pH, rise, a buffer region, and then quite a bit of a, you know, the steepness of the slope here indicating a push in the pH or a rise in pH. And then after the first equivalence, I have at the second equivalence, I mean, I have A2 minus, which cannot react further with OH minus, and thus at the end here, this is where OH minus is in excess. Great, so that gives you the shape of the curve. This on its own looks like a weak acid, and this from this part upwards looks like another weak acid. So it's a diacid. Okay, let's continue with the pH value. The first, like I said, automatically when you have a graph like this, or even without the graph, at the half equivalence, first half equivalence, we get the pH will simply equal pKa1, and at the second half equivalence for a diacid, it's pKa2. And of course, you know where that comes from, but we will discuss it in a moment. Initial pH. Initial pH right at this point. What species do I have? I only have H2A. What is H2A? Yes, it's a weak diacid which acts hopefully as a monoacid, and for you guys in first year, it's only acting as a monoacid. What's the pH of a monoacid? The pH is half pKa1 minus half log C. All the time? No, not all the time. Only when the concentration is greater than 100 Ka1, or when the pH is less than pKa minus 1. So those are the volatiles. That's when you can use this equation. Either check the concentration before and decide to use it, or use it assuming that it's okay to use it and check the pH afterwards. And you'll say, okay, I'm allowed to use it if the pH is less than pKa minus 1. Pretty much the same as weak acids. Pretty much the same as weak acid without a titration at all. Great. Okay, now, as my H2A reacts with any drop of OH minus or any volume of OH minus added, the OH minus in this part, all the way before the equivalence point, is going to be your limiting reagent, and it will tend to 0. It will run out in the reaction. We will have some leftover H2A and some HA produced in this whole region. So we have what? Acid and its conjugate base. And therefore that is governed absolutely by the Henderson equation, Henderson-Hasselbalch. So this whole area for us first year will be governed by Henderson. Once all of the H2A moles have been converted into HA minus, and the concentration of H2A now is equal to the added base, all I have at the first equivalence is HA minus. What is HA minus? Yes, it's amphoteric. What is the pH of an ampholyte? Yes, it's pH equals half pKa1 plus pKa2. And here you don't have to worry about the order who comes first or the pKa's. Now we're done with the first titration curve, and we're going to start with the second titration curve, which is right at the first equivalence all the way to the second equivalence. And so now this acid HA minus is going to react with the base OH minus, and in this area, the base is also limiting. It's not in the excess, it's limiting. And as the HA minus reacts with the limited amount of OH minus, that OH minus will run out, and we will start producing some leftover HA minus, and we produce A2 minus. And so we have an acid and its conjugate couple. And yes, that is governed also all in this whole area by Henderson. Actually, this is better off here, but it doesn't fit best. So this is my buffer region here in this area. Okay. Of course, within the buffer region, whether first equivalence or second, as first half equivalence or second half equivalence, within the buffer region, when A2 minus, for example, equals HA minus, that's when pH equals to the pKa2 in this area. We're done with this whole buffer region, and now all of the HA minus is going to be converted to A2 minus when we add the same amount of OH minus as the moles of HA minus, and we're left in a solution which has only A2 minus at the second equivalence point. What is A2 minus? What is A2 minus? Yes, it's a di-base, which of course it will react as a mono-base for us in first year, and therefore it's governed by the equation pH equals 7/2 pKa2 plus half log C, the base equation, the pKa, of course. Which pKa? pKa2, okay? And watch out because it comes from a POH and pKb1. Now, can I always use this equation? No, only under the conditions where the concentration is greater than 100 Kb1, or assume this equation is okay and check it at the end that pH is greater than pKa2 plus 1. If it's not okay, what do you have to use? The quadratic. Yes, of course, and the quadratic, you all know, comes from the Kb, which is x squared divided by C0 minus x. Once I'm done with the A2 minus, well, once I've created it, now I'm going to add more OH minus after the second equivalence point. Is there another reaction that can take place between the OH minus and the A2 minus? No, there isn't. No reaction. This is a base and another base. This is the mixtures of two bases. And of course, the pH will be determined only by my excess OH, and then the pH at the end will be determined by pH equals, or POH value, and then the pH will be 14 plus log of the OH minus in excess after it's reacted with all the acids in the medium. Great, that's it actually, which is a lot, but this a lot, we've taken every single pH and it's a real very good summary of the whole course, if you will. We have a buffer, we have a weak acid, we have a weak base, we have an ampholyte. What more do you want? Well, I want one more thing. I want to simplify certain calculations, and these are to be memorized by you eventually, and especially if you're going to write the entrance exam for any concours or things like this. The buffer region, which is, yes, easy enough to calculate using Henderson, but then you have to put up a chart to get the HA concentration created and the H2A left over. What is a very nice equation to use is that anytime you're in a buffer region between x equals 0, not at 0, but between 0 and x equals 1, which is at the equivalence point. So if you're in between this region, you're in the what is called the buffer region. And in this buffer region, we can use the following equation. pH equals pKa1 plus log of x divided by 1 minus x. Okay, and the reason I just put these square brackets is that sometimes in your calculator, by the way, you really have to get this separately, or you really have to put square brackets or double brackets to get the correct answer. So you have to watch out for your calculation here. Or get this ratio x divided by 1 minus x and then do the log value of that. I always make a mistake in my calculator with it. Okay, in the second buffer region, which is right here, instead of using the Henderson again, instead of finding concentration of A2 minus created and the concentration of HA minus left over, I can use the second buffer region, which is between X equals 1 and X equals 2. And the pH equals pKa2 plus log of X minus 1 divided by 2 minus X. And all I can tell you is memorize it. Well, actually, the second buffer region is not so difficult. Once I memorize the first, which we've already derived for you last time, instead of X here, put X minus 1. And so here, if instead of X, I put X minus 1 and in brackets minus, you get 2 minus X. Okay? Or simply memorize them. You will see that they come in handy. Now I will continue with the question, which was I just posed. Okay? And this was carbonic acid reacting with OH minus and in different places. Again, we already knew that V at equivalence is 5 milliliters because it occurred when X is equal to 1. But of course, you can do the calculation when CAVA equals CBVB. Moles equals to moles. So this is the concentration of the base, concentration of the acid, volume of the acid, volume of the base at equivalence will be our calculation, which of course is just a waste of your time if you have the X value. Great. At VB equals 0, X equals 0. Okay. That means I have only the diacid carbonic acid, which if the Ka1 is greater than 100 Ka2, then I can react it as a monoacid, which is really, honestly, for our course, this is a useless calculation. It's important for our theory, but calculation-wise, you don't have to do it because we never give you when you have to have the two acids at the same time. Okay, so one is enough to calculate my pH. So I can react this as if it's a monoacid, since Ka1 is greater than 100 Ka2, and then I would say that the pH is dictated only by the first acidity. And what is the first acidity? Well, if the concentration is greater than 100 Ka1, watch out for which Ka, yes, Ka1, then I can use the pH equals half pKa minus half log C, which you all already know. Check it. You have to just check it. Take C divided by the Ka1, see if it's greater than 100, or do this, do whatever you're used to doing now, and continue. If it works, great. pH, find the pH, substitute pKa, substitute C, get the pH value. Now, of course, you can also assume this is correct and then check that the pH is pKa minus 1, but I'm okay with this. At volume equals 2.5, which is half the equivalence point, because if my equivalence point was 5 milli, this is half, but of course the X value already told me that because it's at X equals 0.5. And at half equivalence, that's it, pH equals pKa1. I don't have to do anything else other than just this number, okay? And of course, you know that at that value, we have a hydrogen carbonate. The H2A is equal to the HA minus. When the X is 0.7 or the volume is 3.5, well, here, I actually have to do a calculation usually before the equivalence. So before equivalence, we have the diacid will react with OH to give me hydrogen carbonate and water. CAVA, CBVB, and here I'm using volumes in milliliters and the concentrations or the moles will be in millimoles. It just eases calculation, or the numbers are just easier to deal with when you do that. Do this, of course, the OH before equivalence is what? Limiting reagent. Whatever moles here, it will tend to 0 or call it epsilon, almost 0, because there's a little mini back reaction. But remember, we said that we always react it completely, no matter what the K reaction is. And for strong acids, when you get to higher level, go with the back reaction or see what the K reaction is. But here, as long as I have a strong acid or a strong base as a reactant, it's a complete reaction. What's the leftover H2 carbonate? It's CaVa minus CbVb. Do the calculation. What's the produced hydrogen carbonate? It's simply the limiting reagent moles, which is CbVb. That's the number. Of course, what do you use? We have both acid and its conjugate. We use Henderson. Plug the numbers in. Why do I just keep the millimoles here? Because if I just divide by total volume in milliliters, the volumes cancel, so I don't have to really do it. So pH equals the pKa plus log of the conjugate base hydrogen carbonate divided by the carbonic acid millimoles left over. Great, that's my pH. Well, you know what, to do these calculations, I mean, they're easy and you can do them and they don't take time, but I could make it a lot easier by using the following equation. Okay, that's the equation. pH equals pKa plus log of x divided by 1 minus x. If you don't have the x value, go ahead, find it. It's simply Vb divided by V at equivalence. Get the x value. If you have it, even better. Substitute the x value in. What do you get? Yes, you get 0.7 on the log, and on the bottom, 1 minus 0.7 is 0.3. And when you put it in, guess what? You get the same pH. And I didn't have to do all of this. Great. Next, at x equals 1, which is, of course, my first equivalence. Volume is 5 milliliters. What do I have at my first equivalence? Yes, I have my ampholytic reagent Ha minus, which is in this case hydrogen carbonate. The pH is equal to half pK1 plus pKa2. Okay, so here we have another value. X is equal to 1.3, which has a volume of 6.5. But now this X value is after the first equivalence, and so is my volume of base. So now I've already started the second reaction, which is the hydrogen carbonate reacting with OH minus to produce the carbonate, CO3, 2 minus, and water. Now we're going to put CaVa and CbVb, but no, not the regular CbVb. We're going to put CbVb prime. What do I mean by Vb prime? Well, the volume that I use for the OH is not this whole 6.5. You have to subtract the amount that will react with the first acid to get you to that first equivalence and then beyond. So you always take the volume of the base total, subtract the volume of the base at equivalence, gives you the volume of the base that will actually react with the second acid. Clear? So, and here I'm gonna put hopefully I can fit it in. Okay, so this is Vb prime when you multiply it out. Again, these are in millimoles, so get the concentration. Notice this always stays the same. This is always CaVa, which is the same number of moles. And this is the moles that is, the millimoles that's changing is for the OH minus. So again, in this area, after equivalence point, with the amount of OH minus, only left over after reacting with the first acid completely, this amount is of course limiting, and so it tends to 0. And therefore what's left is this CaVa minus the limited OH millimoles, which happens to be 1.5 times 10 to minus 2. And of course the carbonate that's produced is simply CbVb prime, which is the amount of OH minus reacted or produced carbonate, A2 minus. What do you have left in solution? Yes, you have the acid and its conjugate, which is governed by Henderson. Okay, and substitute then, you have these two concentrations or millimoles, and the pKa value is given, you get the pH is equal 9.95. Okay, well, I'm done. Took me a while, but I could make it easier, right? Or so I'm saying to you, try it. Okay, now I want you to memorize this equation. pH equals pKa2 plus log, plus log x minus 1 divided by x minus 2 minus x. And again, make sure you get this as a ratio alone, not the log of this, okay? So there should be big brackets up here to make sure that this is solve for the ratio first. Again, this is the same that I showed you at the first slide there with my summary slide. And try it here. Let's give it a shot. pKa2 is 10.32 plus log x is 1.3 minus 1 is 0.3. 2 minus x is 2 minus 1.3, which is 0.7. So 0.3 divided by 0.7 is what? Okay, is exactly this number. Okay, you get it exactly the same number. And so you get the exact same pH with zero effort, zero thought process, zero effort, zero calculation, and almost always correct. At second half equivalence, do I have to think a lot? Already x is 1.5, that's second half equivalence. So, and of course you should have also, since the 5 milliliters, let's see, with volumes, it's a little bit harder. 5 milliliters is my equivalence, another 2.5, that's my second half equivalence. Even if you're not given X values, I would recommend you calculate them. At second half equivalence, that's it, pH equals pKa 2. Clear? I don't have to do any calculation, no chart. I don't even have to write this if I don't, if they didn't ask me what do I have as species. So we're done. Whenever my X now is 1.7 and VB is 8.5. So I still haven't reached my second equivalence. And so I'm in this other buffer type region where there's a reaction between hydrogen carbonate producing carbonate, CO3 2 minus, upon reaction with OH, there's going to be leftover HA minus, produced A2 minus, because the OH is again in limiting amount. And I just want to again go through this OH value again. This is the concentration times VB prime, which is the amount, total volume of the base minus the volume at equivalence, because that's the volume that's actually going to react, or that's the moles that will actually react with this second acidity. Okay, use the Henderson because you have acid and its conjugate, substitute your values in, and look here, you have pKa2 again because these two couples make up the second pKa series of this diacid, so you have to use pKa2. All right. Again, this is that. Whenever you have a diacid in the region where you have an X between 1 and 2, try this equation and you will see that you get the same pH. Okay, you get the same pH. Okay, at second equivalence point, we only have carbonate left over, the A2 minus is left, and we actually unfortunately have to calculate its concentration. Not that difficult. The concentration of the A2 minus is CAVA, the number of moles of the acid originally divided by the total volume, which is VA plus total VB, which is 10 milliliters in this case. Go back to the course and we have that in the course, okay? Get that concentration. Now, what do I have to do? What is this? This is a base, right? It's a base. We're assuming that this base, again, acts as a monobase under assumption. And again, I don't have to do calculations, but what do I have to do? I have to check if the concentration C is greater than 100 kB1 for this space. Okay, so I don't have the KB values, but I do have pKa2, because remember, KB is related to the pKa2. pKa2 is 10.32, so 14 minus the pKa2 will be pKb1, and now I can see if the concentration divided by kb1 is greater or less than 100. Turns out that when I check this guy thing, I don't get it greater than 100. It's actually less than 100. What does that mean? Yes, it means I cannot use, and I'm really hopeful, I cannot use my simplified equation pH equals 7 plus half pKa plus half log C. I cannot use it. I cannot do that. I have to use the quadratic. Okay, I have to go back. Well, of course, you don't have to write this, but you have to know what the quadratic is. Which quadratic? Well, the quadratic is KB1 is x squared divided by C minus x. Where did that come from? Yes, it came from the fact that base reacts with water. This base in water will react with water to give me BH plus. In this case, actually, it would be A2 minus, really, reacting with water to give you back the AH minus plus OH minus. But this is the general form for the KB, okay? Okay, so here's my KB. Again, just KB is x squared divided by C minus x, multiply it through, and I still, me personally, I still keep it in this form. I don't like to memorize this one, but you can go ahead and memorize it if you like. Easy for me to derive it right out. Okay, so KB is x squared divided by C minus x, multiply through, you get the quadratic equation, which you have to solve by your calculator. Put everything in. You really have to do the practice with the calculator, guys. I promise you, you will get at least one question of these types of quadratics. And on the concours, maybe more. Okay, so you have to practice the easiest way to do it. Again, this is x squared plus KB, that's my KB. And you can keep it in terms of minus pKb, even in your calculator, minus KB1 times C. Now you can multiply them out, but you don't have to, even in your calculator in the C, when your calculator does it, you will see that this number, you don't have to multiply it out beforehand. It's nice if you do, but you don't have to. Solve for x, and that's it. What is my x? Yes, it's my OH minus. So you can get POH, which is minus log of the OH, which is minus log of the x, and then get the pH from that. It's because you had to use a quadratic. We couldn't simply do our little formula, which we have on the graph. Example of the fact that you can't always use that formula, right? Okay. After equivalence, x equals 2.7 or volume is 13. Okay, so 2V equivalence, this is after it. Again, VB prime, always good to do it. Now take the total volume, subtract the first equivalence, subtract the second equivalence, because I have to use all the OH to react to give me my second base. So I have now CO3 2 minus in solution and OH minus. And like I told you again at the beginning of the graph, these guys will have no reaction with each other. So there will be no reaction. There's no reaction here. I mean, it looks like there is, but there isn't. I'm just showing you, that there is no reaction. This is a mixture of two bases, and irrespective the fact that I have more, let's say, carbonate, it doesn't matter. You always decide on the pH from the stronger of the bases. Now, of course, mixtures of two weak bases is another story altogether, but this is a strong base with a weak base. The stronger base, irrespective of its concentration, will determine my pH value. So the pH depends on the number of moles or millimoles, which is concentration times the excess volume divided by the total volume, which is V of the acid originally plus the total volume of the base. Okay, now once you get that, do the calculation and you get the concentration of OH minus, which is 1.4 times 10 to the minus 3. Now, of course, we want pH, get the POH minus log of that, and then get the pH, which is 14 minus the POH. Okay, and you are done. Okay, I'm going to stop here and I'm going to do the next question in the next